Welcome back. I'm using a new software. I don't really know how this is going to turn out. I can't see where I'm on the screen, so hopefully I'm not blocking anything important. But I'm just going to go through some automotive electrical terms. These are going to be some really basic terms. If you're learning about electrical, this is probably where you need to start because this is going to contain some of the vocabulary you just need to know in order to learn this stuff. So with that said, let's get started. So the first thing here, and I'll put this out there to you. I am currently under quarantine because I have been exposed to COVID. So what I have to do this with is incredibly limited. So I'm going to do the best I can. But here we go. The electricity is the movement of electrons from atom to atom. So if we have, I'm going to use marbles here, we've got like a proton, a neutron, and then around that an electron kind of floats. That's our atom structure. The electrons are what move from atom to atom and give us the phenomenon of electricity. So that's kind of the basics. The electron movement is what is the actual electrical current. Okay, DC current. DC current is a direct current, is the type of current in which electrons flow in one direction. This type of electricity can be stored in batteries and is commonly used in the automotive application. So what this is, DC current, so we get our atom back out there. Our electrons can jump from atom to atom in some cases, and that's where electricity comes from. In DC current, the electron is always flowing the same direction around a chain of atoms. AC, which I don't actually have on here, the electrons actually change directions and flow back and forth. This is DC. DC is probably going to be the most common used in automotive applications, although there is getting to be more AC as time goes on. I still didn't put AC in here. So DC is flowing in one direction. So there's two different theories on that. Some people would say that it flows from positive to negative. Some would say that it flows from negative to positive. And that's just a change over time as our understanding of electricity has changed. So anyway, let's move on. Conductors. Conductors are wires. So we got wires here. And other materials that allow the flow of electricity. Now, pretty much anything will flow electricity if you throw enough voltage at it, but conductors are materials that flow electricity easy. So some common examples of that you're going to see in the automotive world are copper, steel, brass, gold. There's actually gold connectors in cars and places, and probably some other stuff that I'm forgetting. Okay, insulators. Insulators are materials that resist the flow of electricity. Materials like plastic, rubber, and ceramic. And again, if you crank up the voltage high enough, you can pretty well jump through any of these things. But for the most part, like here's our common wire. We've got a copper core and then a rubbery plastic material for the outside that is our insulator on the outside to keep the electricity inside this wire. Now you could actually run wires without any type of shielding. You just have to keep them away from anything that will actually jump electricity too. So they wouldn't be able to rub on metal or anything like that. A good example of that would be like an electric fence for cattle or horses or whatever barnyard animals you've got. All those wires are bare, and as long as they don't touch ground, they can carry electricity. All right, a semiconductor. This one is actually kind of complicated, and I'm going to stay out of that. So I'm going to keep it really simple. It's a substance that is capable of working as both a conductor and an insulator. And we'll get into one of the real common areas that they're used in automotive later. Actually, there might be two farther down this presentation. I can't quite remember. Current. So the current is the amperage or the volume of electrons flowing through a conductor. So this is the amount, so if we go back to our example, the amount of electrons that are flowing around, that's going to be amperage. Voltage is the force or electrical pressure that causes the electron flow. So when I said earlier that anything can conduct electricity if the voltage is high enough, that's because voltage is what pushes those electrons through the material. Now, there's this common conversation that as far as what kills you, so electricity can kill you. Now, one of the conversations that you can have is what kills you, current or amps or voltage? And most people will say that amperage is what kills you, not the voltage. But here's the thing: an automotive battery carries far more than enough amperage to kill you, yet I can go up and grab a post on each side of that battery with my hand and nothing happens. Why is that? Because it's only at 12 volts. At 12 volts, my body doesn't flow enough of those amperage. The At 12 volts, my body doesn't flow enough of those electrons or amps through my body to actually kill me. So yes, it is kind of the amps that kill you. It's kind of the voltage, but the reality is you have to have the presence of both. Okay, resistance, and I kind of said this one already. So in the example I just gave and what kills you, resistance is what is opposing the flow. So in the case of grabbing onto a 12-volt battery, your body is opposing the flow of those electrons and not letting them flow through at a high enough rate to kill you. Turn that up to like 60 volts, and all of a sudden, now you've got a problem. So another way to think about resistance is it is the load in the circuit. So I don't even have a battery to hook this up to, but if I did, this LED fog light work light, this would be the load in the circuit. So we could take this red wire, take the red wire, hook it to the positive, the black wire, hook it to the negative, and this light would light up, and the electrons flowing through here, the light is the resistance in the circuit. So the resistance should be wherever the work is being performed by the electricity. And sometimes it's being performed where you don't want it to be. But where there's resistance, the electricity is doing work. So a series circuit is a circuit with more than one load connected in a single electrical path. All right, and again, hopefully I'm getting this in frame, but here's our battery. So this would be in an automotive series, or this would be a series circuit with an automotive battery. This is the electrical symbol for a battery. That would be a 6-cell battery or a 12-volt battery. So as you come down, here's our first light bulb, here's our second light bulb, and then it comes back around it into the battery. If it doesn't come back around, it doesn't work. So this would be a series circuit. There's more than one load, light bulbs, connected in the single path. This is pretty uncommon in the automotive world at this point. Once upon a time, they would use stuff like this for warning lights, turn signals, things like that, but it's more or less gone away now that we have as much electronics on the car as we do. So up next is a parallel circuit, and I'll switch this up so it's a parallel. Okay, so in a parallel circuit, what we've got, this is a circuit with more than one electrical path. And I should have done this when I was still on series, but if we had our series set up here, if one of those light bulbs would have gone out, they both went out. So a parallel circuit, what you've got is, we'll say, and I don't remember if this is the actual way this symbol is written or not, but let's say this is our positive. We've got 12 volts here. Got 12 volts to come out to this light. It goes through this light. This light gets the full 12 volts. I really hope this is in frame. And then it comes back around to the ground and comes back into the battery. Same thing comes over here. We've got 12 volts at the top of this light bulb. We use the 12 volts across the light bulb. It comes back and goes back into the battery. So this is a circuit with more than one electrical path. Now a series parallel is a circuit that has both a series and a parallel circuit. So there's a couple different ways that we can do that. And That was bad, but you get the idea. So I add another light bulb there. The electricity first goes through this light bulb, and then it goes into these two as a series. We could also put it down here so that this one is kind of on its own. So that this one is kind of on its own. It gets 12 volts. It's a parallel, and then we have a series for the other one. So that would be a series parallel. It just happened. So Ohm's law is a simple formula for calculating voltage, current, or resistance when two of the three are known. So that would be resistance equals voltage divided by current. Now different places will use different symbols to represent these. But for this example, we'll just do resistance equals volts divided by amps. Now, depending on what situation you're using, they may call resistance a few different things. Voltage can be voltage or intensity. Current can be amps or I can't remember. But there are different terms that can be used to express all of these. But this is the basic formula. This is Ohm's law. I don't have a light switch, but you guys all know what a rocker switch is. You flip a switch, that's a switch. It either lets current flow through or doesn't. So that allows a circuit to be turned on or off. A short circuit. So this is an accidental low resistance connection that results in excessive current flow, which will typically result in overheating or fire if the circuit is not protected. So what a short circuit is let's say I've got my piece of wire here. This is, say, the power wire to a light bulb. Somewhere along the line, it rubs through and touches the metal chassis of the car, which is ground. This would be a short circuit because now the electricity has a direct path back to ground. A fuse is one of those things that we can use to protect a circuit from damage in the event of a short circuit. So if we want to protect our wire, if we just have this hooked, if I hook this directly to the power and the ground in a battery, it will smoke, it will potentially light other stuff around it on fire, it will get incredibly hot, and a wire this small will get incredibly hot incredibly fast. Now, a fuse, and this would be a 15 amp version, a fuse has a spot inside of it that is properly sized that when this sees over 15 amps flow through it, the spot in the center blows out and it stops current flow. So if we have the fuse hooked on to the front of the wire and it rubs through down here, a bunch of current will try to flow through and it pops this fuse and it stops it. So if you have a vehicle that fuses, I hate to say this, but fuses do sometimes get old and kind of corrode inside and blow for virtually no reason, but that's not usually the case. Typically, if a fuse blows, you've got a problem. So that turns into diagnosing wiring systems. Okay, a fusible link, and I don't have an example of this, but we can kind of use this wire. And actually, I think this is, you're not going to be able to see it on camera, but this black wire is smaller than the green wire. It's smaller around. So what a fusible link is a piece of specialized wire that is smaller than the circuit that is protecting. This usually comes straight off a battery. So you'll have your fusible link hooked directly to the battery or very close to the battery, and then it connects, and then it protects the wire that feeds power back. Usually it's pre-fuse box. So you'll have the battery over here, fusible link right off the battery, and then a wire that runs back to the fuse box area. Those are used to protect wires before they go into a fuse box where a bunch of fuses are. So in the event that you get too much current flowing through, the fuse pops. Well, a fusible link actually melts in half. And the special insulation that's used on that kind of contains it. In fact, sometimes when they pull, when the fusible link burns up, you actually pull, and if it's stretchy, that means the copper inside of it's gone, and that fusible link is burned out. The other side, the other positive to that is it can withstand short bursts of overcurrent without blowing out. So let's say we have something like we have an electric motor that's going to run pretty consistently, and it draws double the amperage when it fires up. So when it fires up, it draws 30 amps for just a second and then drops back down to, say, 15 amps. A fusible link can handle that where a fuse would not be able to. Okay, a circuit breaker. I really don't have one of these, but they're kind of similar to the circuit breaker that are in your house. What they do is basically the same job as a fuse. It's also circuit protection. It disconnects the circuit from a power source. Breakers can be reset automatically or manually when current returns to a normal level. I use these a lot on trailer brake controllers. So if you've got something that you really don't want to have no current to if a fuse blows, like a brake controller for electric brakes on a trailer, a circuit breaker is a more expensive but pretty decent option for that. And automatically resetting one, as soon as the current drops back down, it kicks back on and you have power again. They used to be used on power windows a lot. So when your power window would go all the way up and you keep holding the button, it shuts off power to it. And then when it was all the way down and you kept holding the button, it would shut off power to it. And then it would reset and come back on. All right. A relay is an electrically operated switch. They use low current. They use a low current control circuit to operate a high current circuit. So here's a relay. Now, what this would be used for is 2 of these are the control circuit and 3 of them are for the actual load in the circuit. Now, what we do is we use the control circuit as low amperage, so you can use just a normal switch. And then this would be used, like this one is a 40 amp relay. This one can handle a continuous 40 amp load. So if you have a high draw item, like say a cooling fan, you run it through a relay, you use a switch to turn it on, the relay then takes the heavy load of the circuit and can handle it safely, whereas switches are hard to get in a 40 amp rating. Okay, diode is an electrical check valve. So we already covered that the electricity is the electrons flying around. So in a DC system, our electrons always travel the same direction around the wire. What a diode is a device that actually blocks. So let's say we have a magnetic field collapse. It'll send the electrons back the other way. Or if we have, these would be used in alternators to convert them from alternating current, alternator, to DC or direct current, which is what most of the car runs on. They block the electrons from going. So let's say this little red piece of tape was the diode. It would allow the electrons to flow one direction, but block them from coming back. Okay, a jumper wire. Honestly, this kind of is a jumper wire. It's simply a wire that can be used to bypass switches, relays, or other components when testing. You can get fancy jumper wires. I never have. I've simply just used scrap wire most of the time. Sometimes you have to get actual like good relay, or sometimes you have to get good connectors for the end so they can actually handle that. But it's just a jumper wire. Okay, test light. I also don't have one of those. But I'll use this tool. I'll use this as kind of an example. So a test light usually looks kind of like a screwdriver. It's got an incandescent bulb, not an LED. The LEDs only flow electricity in one direction. If you hook this up backwards, it won't work. So what a test light is it's basically a screwdriver-looking handle with a light bulb in it and a wire out the back. Why am I not showing you pictures of this stuff? Copyright laws. And I don't have a test light on me right now, so I can't show you that. But Google it. It looks like a screwdriver with a light bulb in the middle and a wire coming off. You hook one end to either power or ground, and that's why they're not LED, because you can hook them up either direction and test for power or ground, depending on what you're trying to figure out. Yeah, voltmeter. Don't have one of these either. It's a meter. I do, however, have some leads. So these leads would be off a different old school meter that I've got. A voltmeter will have probably more modern, but leads kind of looking like this. They're used to check voltage in a circuit. just as the name implies. An ammeter. I actually have this old school unit here. This is an amperage. So we've got amps, ohms. Depending on where you set this one up, there's either an amp meter or an ohm meter. And I'm not going to go through how to hook these things up right now, but the amp meter is a really easy to function. It's really easy to break the ammeter function if you don't hook it up right. So I'll probably do a video on that at some point in the future on how to use an ammeter, but do a little research before you hook up an ammeter or you can blow the meter. Okay, an ohm meter. This is used to measure resistance. So again, the same deal. You've got these connectors, depending on, you hook them up properly and you can read the resistance in a circuit. Okay, digital multimeter. And this is what pretty much everyone is using right now, unless they're using a lab scope. But a digital multimeter is usually like yay big. Some of the common companies that make that would be Fluke, Snap-on. I have a Radio Shack one, but it's not here, so I can't show it to you. There's all kinds of different companies. I'm not going to try to list them off, but those are 3 that I've used. So they combine a voltmeter, ammeter, and ohm meter in one tool. They have a digital readout and are extremely useful for electrical diagnosis. In fact, if I'm taking a long road trip, I usually throw a DVOM in, because if I have a DVOM and some limited wiring resources, I can kind of figure stuff out and fix it on a lot of my vehicles, especially the older ones. Okay, a wiring diagram. The schematic that shows how electrical components are connected with wires. This is a real simplistic wiring diagram. So that's it for this one. Hopefully the stuff that I had there showed up, and I'm really not sure that it did, especially the stuff that I was like drawing right about here. But anyway, thanks for watching, and I'll see you later.